Greetings everybody. This video will hopefully explain part 5 of the chapter 7 lecture notes, where we're going to do conservation of energy and friction. Now we're not going to ignore friction. So remember, without friction, i.e. in the absence, meaning if there are no non-conservative forces, if there's no friction, then conservation of energy is written like this: KE initial plus PE initial equals KE final plus PE final, where the PE could be gravitational potential energy mgh and or spring potential energy 1/2 kx squared. Okay? And again, you have your reference point, which only applies to gravitational potential energy. Now, what if there's friction? Well, all we do is we take the conservation of energy equation, and we make one change to it. Well, we have to take the conservation of energy equation and we have to modify it to indicate the energy loss due to friction. And I write it as minus EFR, where EFR is the work done by energy, or equivalent, EFR is the work done by friction, i.e. it's the energy lost due to friction. Remember, work done by Fk is always negative. Hence, that's why I have the minus sign right there, because the work done by friction is always negative. So you always modify the left side of the COE equation. You take KEI plus PEI minus EFR equals KEF plus PEF. Or again, potential energy could be spring and or gravitational. Now, what is EFR? Well, again, what is EFR? EFR is the work done by friction, or if you equivalently, the energy lost due to friction. Because generally friction takes energy away from the system. You slide down, if you're sliding down an incline, you slide down slower the more friction there is, because the friction between you and the incline, that friction is taking energy away from you, i.e. away from the system. So the work done by friction is always negative. That is where this minus sign comes from. Don't do a double negative. EFR itself, just calculate EFR according to this. The negative sign is taken care of right there. Now, what is EFR? Well, it's Fk. Remember, it's the work done by friction, or the energy lost due to friction. It's friction force times distance. It's FKD. Well, what is Fk? Fk is always mu k Fn. However, remember, Fn depends on the geometry of the problem. The normal force on an object on an incline is different than the normal force of an object on a horizontal. But EFR is always FKD, and Fk is always mu k Fn. Well, let's look at this example. You have a 3 kilogram crate sliding down a ramp. The ramp is 1 meter in length, meaning it's when it's on the ramp, it's going to slide a distance of d equal to 1 meter. The ramp is inclined at 30 degrees. The coefficient of friction, of kinetic friction between the crate and the ramp, is mu k is 0.196. The crate starts from rest at the top, and once it hits the bottom, it continues to move a short distance on the horizontal before coming to a stop. Just like the problem on exam 2. The penguin slides down the incline, then when he gets to the bottom, he moves along the horizontal for a certain distance and for a certain time before it stops. Well, let's use energy methods to determine the speed of the crate, Vf, at the bottom of the ramp. And there is friction, because you're told right here, hey, there's kinetic friction between the crate and the ramp. All right. Well, we know that Fk is mu k Fn. Now, in this case, remember, again, exam 2, Newton's second law, and specifically for an inclined plane problem. We don't need to reinvent the wheel. We know for this particular example, Fn is mg cosine theta. Remember, the y component of mg is mg cosine theta. The x component of mg is mg sine theta. So here, and I didn't draw Fn in, but you could. That shouldn't be a big stretch. So Fk is going to be mu k Fn. It's going to be mu k mg cosine theta. Let's choose the bottom of the ramp as the reference point, meaning that's where the gravitational potential energy is 0. Well, let's start with the conservation of energy equation. I'm going to write it in its entirety. Ke initial plus Pe initial minus EFR equals Ke final plus Pe final, meaning final when the crate is at the bottom of the ramp. That's okay. Well, initial kinetic energy is 0. Why? Because the crate starts from rest. So Ke initial is 0. Well, what's the Pe initial? Well, the Pe initial is mgh, where h is 0.5 meters. See in the figure, the crate is at a height of 0.5 meters. Remember, because I'm choosing the bottom of the ramp as the reference point. So let me go ahead and indicate that. Let me pause this for a second. Okay, so we know, just to recap, we know for this particular problem, Fn is mg cosine theta. And Fk is always mu k Fn. So Fk is mu k mg cosine theta. Now let's choose the bottom of the ramp as the reference point. The green dotted line right there. Remember, by definition, that's where the gravitational PE is 0. Notice that means that the crate starts off at a height of h above the reference point. And h is given as 0.5 meters. Okay, so let's apply the conservation of energy from the top of the ramp to the bottom. Notice, again, the crate starts from rest, V initial 0. When it gets to the bottom of the ramp, it's moving with some speed, Vf. So we have, again, the conservation of energy equation modified because there's friction. Ke initial plus Pe initial minus EFR equals Kef plus Pef. Well, what's the initial kinetic energy? 0. Right there. Vi is 0. So there's no Kei term. What is Pe initial? Mgh. The crate is at a distance of h above the reference point indicated by the green dotted line. So that's the initial PEI is mgh, and we have minus EFR. So we have minus and minus. Well, what is EFR? It's FKD. It's the kinetic friction force Fk times the distance d it slides along the incline, because there's friction between the crate and the ramp. And the crate slides a distance d along the ramp. So friction force, EFR is FKD. Well, what's the final kinetic energy? Well, the final kinetic energy is 1/2 mv final squared. What's the final potential energy? Well, the final potential energy is 0, because when the crate gets to the bottom of the ramp, it is at the reference point, meaning there's no gravitational potential energy. So the right-hand side, so we have our energy, our COE equation, the right-hand side just becomes 1/2 mv final squared. Well, now let's look at mgh. What's Fk? Well, Fk is mu k mg cosine theta. So in parentheses, what is Fk? Mu k mg cosine theta. Then you have the d, and you have the d. That's why I want to use parentheses. Then on the right-hand side, I have 1/2 mv final squared. Well, solve this equation algebraically for Vf. Nothing complicated. The masses cancel, multiply by 2, take the square root. So you get this expression for Vf, 2g, under the radical you have 2g parentheses, h minus mu k d cosine theta. And you know g is 9.8 meters per second squared. H is the 0.5 meters. Mu k is the 0.196. D is 1 meter. Cosine of 30, plug that all in. Make sure you're in degrees mode. You get 2.54 meters per second. Now, so the Vf at the bottom of the ramp, just like the penguins sliding down the ski slope, the final speed at the bottom becomes the initial speed for the horizontal. And we want to know, again, this becomes VI for the horizontal part. And I want to know if the coefficient of kinetic friction is the same on the horizontal part, how far does the crate slide before coming to a stop? Well, I want to apply conservation of energy from when it first gets to the bottom of the incline, then it's sliding along the horizontal until when it stops. Now remember, on the horizontal, Fk is always mu kFn, but on the horizontal, Fn is mg. So on the horizontal, Fk is mu kmg. Now remember, we're only on the horizontal part, so we don't have to worry about an initial and final potential energy, because the height, when it's on the horizontal, the height of the crate is not changing. You know, what happens is it gets to the bottom and then it begins to slide in the horizontal, along the horizontal, until stopping. So we don't even have to worry about PE initial or PE final on the horizontal, because the height of the crate is not changing, so we don't care about the gravitational potential energy. So we can just set them both equal to 0. Now again, I'm writing out, here's the complete conservation of energy equation with friction. Now remember, the kinetic energy, the initial kinetic energy on the horizontal is 1/2 m VI squared. But VI, remember, VF for the incline becomes VI for the horizontal. Okay, so I know VI. So I have the initial kinetic energy, 1/2 m VI squared. Again, PEI gone, PE final gone. KE final is 0 because it comes to a stop. Okay, so the right-hand side is 0. Now what is EFR? Well, remember, here's the minus, here's the minus. What is EFR? It's FKX. I'm calling the distance along the horizontal, I'm calling that distance x. And EFR is always FK times distance. So on the incline, EFR was FKD. On the horizontal, I'm calling it FKX. I'm saying nothing complicated. The crate slides a distance of x along the horizontal before coming to a stop. And I want to know what is x. Well, so I have 1/2 m VI squared minus FKX equals 0. Why is the right-hand side 0 again? Well, the PE final 0 and the KE final 0. Why is the PE initial 0? Well, because on the horizontal, the gravitational potential energy never changes, so we don't even really need to worry about it. So initial kinetic energy, 1/2 m VI squared minus EFR minus FKX equals 0. What is FK? Mu kmg. Solve for x. X is equal to VI squared over 2 mu kg. You know, remember, the initial speed at the horizontal was the final speed at the base of the incline, so that's your VI, it's 2.54. Mu k was the same, 0.196, and G is 9.8. You get 1.68 meters. I'll do example 2 in a separate video. I want to keep these videos manageable, so let me do example 2 in a separate video.